Now finally, we will quickly cover the randomized incremental algorithm to compute a 3D convex solve. The basic outline of this randomized incremental is very similar to other randomized incremental algorithms we've seen before. The first step is to randomly shuffle the points. The second step is essentially just initialization step. So in this case, the smallest meaningful convex solve that we can have in 3D is obtained by having thereby the convex solve of 4 points. So given 4 points, this will define essentially a prism, and that is the smallest convex solve we could have in 3-dimensional space. And then we will insert the remaining points one by one. However, the details of this insertion is what makes this algorithm interesting. How do we insert the next point pi? We make the following observation. To insert point pi, we first need to find the faces that are visible from pi. Those faces must be removed. So all these darkened faces must be removed since they are visible from pi. Then we have to find the boundary between visible and invisible faces. These boundary edges define the new faces that must be added to the convex solve to get us the new updated convex solve, like this. How can we know a face is a boundary, an edge is a boundary edge? Simply by just checking the two faces next to it. If one of the faces is visible while the other one is not, then that edge is a boundary edge. So in a sense, it's obvious that finding just visible faces is sufficient to find all the boundary edges and update the convex solve. As a result, how do we find? We just need to find the visible faces. To find the visible faces, use the following idea. It's a very simple idea. It's only the analysis level that is complicated. So for every input point, we maintain the list of all the faces that are visible from P. This means that when I go back here, for this point Pi, I actually had the list of all the faces that were visible from Pi. So this means that I don't need to do anything at this step of the algorithm. I just have them for free. Conversely, for every face, I maintain a list of points that can see this face F. And also, to be able to update these lists efficiently, I will keep pointers between them. In other words, for every face in the list, for every face that is visible from point P, I put a pointer to the point P that can see face F. So let me go through this again. So consider face that is inside the list of LP. This means that P can see F. Based on the second definition, inside the list of F, I have included point P because point P can see F. I will keep bidirectional pointers between these two entities. So these two lists can be easily updated. If I want to remove a point, if I want to remove a face, I can simply remove the copy of the face as well as its copy inside the list of LP. This will allow for updates to be done in constant time without having to search through the list every single time. So the only thing I need to cover is that how do we update these lists every time I do an insertion. Remember that the faces visible from P are now available for free. So that means the only thing left to do is to update to have this information for the newly created faces. Let's look at one newly created face. Let's say consider face F that was created using this boundary edge, and I had a visible face F1 and invisible face F1 and a visible face F2. The main observation that we can make here is that the list of points that can see face F is a subset of the list of points that can see either F1 or F2. In other words, every point that can see F must either see either F1 or F2 or potentially or even both. As a result, if I have the list of these two lists, I could go through them and I could update the list of all the points that can see F. Turns out So the time that it takes to this update is essentially proportional to the following summation. So fi is a list of faces visible from P, including their boundary, their adjacent faces. So technically, I should make an adjustment here, including those two visible faces. Yeah, so fi includes all the dark blue faces as well as all the faces that are adjacent to these dark blue faces. For every f in this phi, LFI is the list of points in it, so it is a point that can see f. So that means to update the list of all the faces that are created by these points, I simply need to go through all of these lists once. This is the asymptotic time to create all these lists. The difficult part is actually to show that these lists cannot be too big. Using some slightly more complicated backwards analysis, we can show that it takes roughly n over 8 time on average to insert the right point. Summing them up for I equals say 5 to n will give us the n log n expected running time.